Okay, I'm gonna try to do the experiment for week 10, the one I distributed to you, and rather than go through the folder all of last night, I did, by the way, solve that problem of how to show the camera, not just as a small image, but show it so that I could show you the experiment. That's what's going to happen here in this. You're just going to see the whole camera, and I'm just going to show you some instruments and maybe let you look at some that might matter. And I'm going to keep this to a bunch of short videos, and we'll work our way through the experiment. You can replay videos as you need to fill out the experiments, but this is going to be a practice way of doing a demo. I'm going to show you equipment that, if I can make it available to you in a pack, this is what will be in there. So you might want to come back to these videos for setting up. If we are able to do that, I've pretty much decided handing out, recovering the stuff is getting more difficult every day here. But if some of you want to do that, I'm not going to be able to require it. That's going to end up too much of a nightmare for us all. But I don't want to eliminate the possibility from some of you. So here was that oscilloscope that I talked about. This is called a picoscope. Whoops, upside down. So if you get one, you'll get it with a label, and you'll have a whole set of equipment that all has the similar label. Here's a close-up look of that piece, right? So you can actually read the labels. These are called BNC connectors. You're familiar with them. It's the stuff you've had on the DC power supplies at school. So on this AWG, this is called an arbitrary waveform generator. The important thing you need to know is this is going to generate a lot of different waveforms that you can pick and choose. Arbitrary just means you can select one, and in the real fancy versions of this, you can actually combine waveforms and make something pretty complex. Here are two different input channels, so you can observe, you can measure two things simultaneously. A channel and B channel. The A channel is blue, the B channel is red. Okay, now in order to run this just plugs into a USB on your computer. But in order to run it, you have to have an app. And this is that app. Now, for someone that wants to, this is that app. We saw this a little bit before, but it's Picoscope 6. You would have to download this on your computer. It's free and so forth. And I could do a simple video, or it's very simple instructions on how to download that. So there's the blue signal, and it's just vibrating around 0 because there's nothing on it. There's nothing connected here to the terminals. So I'm going to do a couple of things. The first thing I'm going to do is just take a short BNC to BNC connector, and I'm going to make it come out of the signal generator and into the A input. Okay, so I've just wired the signal generator directly to one of the input channels A. That's this blue one. Now you notice the thing that happened immediately is this vibration went up, this noise went up. Let's just, before we do anything, get an idea of what's there. There's the 0 line right here, where my pointer is. This is minus 10 something. What is it? Well, it's millivolts. You see it up here. It's millivolts. So this isn't much. This is about minus 5 millivolts, which we would call noise. And the fact that it's vibrating around would be just noise. Compare it to a simple AAA battery, and that's almost nothing. The time base down here, notice is 0, 20, 40, 60, 80. This is in microseconds, and nothing has been set up. Up here is the A channel setup, where you can set up, I'll show you, you have all kinds of possibilities. You can turn it off, stop it from inputting. You can have it on auto where it kind of tries to do stuff on its own. Or you can pick a voltage level, right? I'm just going to pick plus and minus 2. So what happened was I changed the value of the maximum level to 2 volts, not whatever it was, 40 or 50 millivolts. It's 2 volts. So if I had a 1.5 volt battery, it would show up right about in here. Now the 0 looks more like a 0 and it looks cleaner. This is because we've just changed the scale of the oscilloscope to be coarser than we had before. The time frame is still 20 microseconds per division. You see it up here where my pointer is. And that's the distance between spaces here. So there's 2 different approaches. One is if I set the oscilloscope, I set the maximum value of the display, plus and minus. So each of the grid marks is 0.4 of a volt. If I set the time base, then I'm setting the volts per division. And if I look down, you'll see, oh, there's a lot of choices there. I can slow it down to where I'm looking at 5 seconds per division, which is, look at it, it hardly moves. This is just collecting data now at a very slow pace, right? I can speed it up to collect it at a 1 second rate. Now it collects all this, the same process is going on, it's just collecting faster. Okay? I still have no signal. I've connected the 2 from the waveform generator to the input A, but I haven't done anything with this to turn it on. Here is that thing. Here's the AWG. Notice if I just highlight it, it says, oh, that's a signal generator. Well, let's turn it on and see what it is, right? Well, I won't put it over me so you can see. But here's the arbitrary part. So you can create arbitrary waveforms. You can just make them up. All right. Here's a switch that turns it on and off, whatever it is that you're going to do. And here are the choices. I can set the frequency. And notice it says starting frequency because one of the things I could do is have it scan through a bunch of frequencies. If you were testing vibration in a car, these would be fairly low frequencies, but you could run a machine that changes the vibration on the car at a fixed rate. Here's an amplitude and here's an offset. Let me show you a little bit of what each of these things do. One other thing, I can choose the type of waveform that I want. Here's a sine wave. That's what we've been studying. That's AC. That's alternating current. Here's square waves, triangles, ramps, ramping up, ramping down. Sometimes we call those sawtooth. Here's some other fancy ones that are strange. And then here's a DC source. So you can use this one output to create a lot of different waveforms. Okay, it's a pretty versatile device. Costs $139, by the way. You can get them on Amazon or any place. And this company, Picotech, makes a whole bunch of these things, including a bunch aimed at automotive and electrical. But they all revolve around this basic technology. So I'm going to choose the sine wave, and I've got 1 kilohertz. That's the number that's in your setup, part 1 of the experiment, 1 kilohertz. And the amplitude is set for 1 volt. And I have the page of the experiment here, and it says, set the function generator for 1 kilohertz and 2 volts. So I'm going to do that, right? I just hit the dial. You can dial it up. It goes down to 1 volt, and it starts walking down in millivolts. You can also go right in here and type in 2 volts. Okay? And offset, I'll show you what that means in a moment, but that means I can move the 0 line up and down, right? So I'm going to turn this on and see what we get. And so far we got nothing. Why is that happening? It is a sign. Here we go. Okay, now isn't this weird? I'll turn that off. That doesn't look like a sine wave, does it? No, it's because the sweeping is so slow. Look at, I've got the sweep up here at 1 second per division. So while the sweep is moving at 1 second, see, 1 second per division, well, that's a lot of frequency going on. All we got to do is start to speed this up. Well, that's slowing it down. All we got to do is start to speed this up a little bit. Oh, look at more show up. And watch the lower axis down here. It's changing as I speed this guy up. Notice the top of the signals is up here at +2 and -2. That's what I set on the signal generator. Right, I can maybe keep that over here as a reminder. There's our 2 volts. And now as I speed this thing up, it's looking funnier. We're starting to see, maybe if we stretch it out enough, hey, here it's starting to look like a sine wave if it would only sit still long enough for me to know what's going on. The way to get it to sit still is to activate a trigger. And the trigger says, I want to start at some point making traces. Here there's no trigger. Let me just put a crude one in and say, well, I'll let it trigger on its own automatically. Notice it stopped immediately. Here's the trigger. And here's 0 time. So all the time before the trigger is called negative time. And we're at 500 microseconds per division. So that's what the 0.5 means. 0.5 milliseconds. Right here it's showing us milliseconds. So minus 0.5, that's 500 microseconds went on during that time. Here's another -1. So 1,000 microseconds went on during that time, and that's 1 millisecond. So you want to go back and look at micro and milli and regular and find out what those exponents are. 10 to the -0, 10 to the -3 for milli, 10 to the -6 for micro. Okay, well, I'm going to take this down one more level, speed this up here. So now I can see this. You cannot do this on most oscilloscopes, but I can grab and drag that around a little bit and say, what if I want to trigger up here? Oh, I can trigger up there. Look at that. And you can't see it too well now in this but it moved the 0 point. Now watch, I'll drag this back over to the center line, and it still isn't exactly 0, right? But it's triggering on that point. So you can play with this a lot, and it's kind of fun. But the basic auto triggering is going to be here at 0, 0, and I wasn't able to replicate it, right? So I'd have to be careful. Notice also when I click on that. Here, if I take and just right-click somewhere on this waveform, whoops, it gives me a bunch of options. But more importantly, if I just hold the pointer there and left-click on it, it tells me what the time and what the value of the signal is at that point. It's 758.8 millivolts. So where's that? That's not quite 0.8 of a volt. And that occurred at 65.77 microseconds. Ton of information here. What have we got though? Here is one whole cycle. Tell you what, I'm going to scale this down just a touch. Here's a nice clean waveform like you're used to seeing. So there's 2 volts plus, 2 volts minus, and it ends right there. Okay? So what is this time? I'm going through 1. Let me maybe reset it so where it lines up perfectly. Right? It didn't line up where I want. This is one thing. Once you start messing with the triggers, well, I'm going to quit while I'm ahead. But look, here's 1, 2, 3, 4, 5 divisions. 5 divisions at 200 microseconds per division. So 5 times 200 is 1,000 microseconds. This distance is 1 millisecond. So the period of this waveform is 1 millisecond. And it kind of says that down here. So I encourage you to just kind of, you can look at this video and stop it and check the numbers out for yourself. But that's 1 millisecond. And so this is 1 period. So the frequency must be 1 divided by 10 to the minus third, which is 1,000 cycles per second. And that's where we set it, at 1 kilohertz. Okay, so that whole first step, that whole first piece of setting up the source, I've just done for you. Drawing the waveform is this. I can put this up maybe. No, I'm not getting a good one. But I encourage you to draw the waveform. Make an attempt at drawing it. I do want to show you a crude drawing, yeah. So here you can see it. This is what I made by hand of this picture. Notice when I say label the vertical axes, I put numbers on there. 0, 2, 4, 0, minus 2, minus 4. And I drew the waveform. There's the 500 microseconds, 100 microseconds per division, and 1 millisecond. So when I drew this picture, I drew this back half from what would have been 0 if I'd have left it alone out to 1 millisecond. I drew that back half. That's all I'm asking for. Now when you go to mount it or put it in the lab, you have a fillable PDF. The way to do this is you will need to open up and do your filling with this. Now a lot of it you can fill in just by writing it, opening in a preview or whatever your computer does, and you can start typing in. But when it gets to putting in a graph or something that is more pictorial, you will have to take a picture of this. And, I just did this on my cell phone. I can pull that up real quick. Let's see. It is here. Whoops, I'll flip it over. So here's my version of this. This is a picture of the drawing I just showed you. And this is a JPEG image. And what I can do is, when it comes time to put this image in the file you're going to submit, the fillable form, you must use this version of Acrobat Reader. Let me open this up. You have this. This is a free version. If you don't have it, you can download it for free. Adobe always asks you to do this. And here I've got the lab, same one you have. And I'm going down, and I've asked you to attach it at the bottom. So the picture that I just drew right here, right, I've attached, here's a blank. And what you can do is, it will ask you, where's your image? Select an image to put in there. Well, I'm going to browse and find that image. This should be it. I will open it. Oops, that's the one of the Pico. But you saw the process. I mean, I can actually go in. Maybe I can delete that. I'll just try to write over it. Browse. I'll go back there and put in 364. And there's that image. Okay, so it will do that and fill that nice big space so I can see it. That's how I want you to do the lab. And I've gone longer than I want here right now, but at least you learn something about the oscilloscope. And I will post this on YouTube and send you a link. And this essentially, not essentially, this is the first part of the lab, source setup. I will do some similar videos for the part 2, where we take a simple circuit and apply an AC signal. So, till the next time, I'll catch up with you. Thanks. And thanks for your patience last night. That was frustrating for me, and I'm sure it was for you. But we'll get past it. Thank you.